Chemical engineering companies of the past have had many hurdles to clear in the field of reactor design. The complex calculations and high capital cost of experimental units strained the iteration process and limited the meaningful development possible in designing reactors. Two technologies are changing the face of these engineering operations: finite element analysis and 3D printing. Finite element analysis programs such as COMSOL alleviate the complex calculations with a computational engine built to apply transport and kinetic principles to any geometry. Instead of a revised 3D model adding to the backlog of required physical calculations, COMSOL simply requires the upload of a new STL file to handle a new geometry. Desktop 3D printing resolves the high capital cost problems using cheap material and fully automated assembly. Rather than needing to contract a new reactor construction for each iteration, these printers can construct reactors in a matter of hours to the precision of the engineer's CAD model. Formlab stereolithography printers generate the watertight cross-linked reactors necessary for liquid reactors. Between COMSOL simulations and 3D printed models, new reactor designs can be rapidly produced and tested. Our group went through 2 designs to demonstrate this process. In this experiment, malachite green and sodium hydroxide are the reactants. The reaction begins with a colored solution of concentrated malachite green getting mixed with sodium hydroxide. As it proceeds, the solution becomes clearer. It proceeds following this rate equation. Rate equals K times the concentration of malachite green times the concentration of sodium hydroxide. However, since the concentration of sodium hydroxide is so large, it can be assumed to remain constant throughout the reaction. This allows the rate to simplify so that the concentration of malachite green is the only variable in the equation. Rate equals K times the concentration of malachite green. Since this reaction is highly dependent on mixing of both species, the fluid dynamics of the reactor plays a big part in reaction rate and conversion. At the scale of these experiments, flow is limited to the laminar flow regime. In this zone, the dimensionless number known as the Pecklet number can be used to show how much mixing occurs as the fluid flows down the reactor. The Pecklet number is a ratio of the ejective transport rate to the diffusive transport rate. In purely diffusive mixing processes, the characteristic length for mixing is proportional to the Pecklet number. A linear relationship between the mixing time and the Pecklet number implies the channel length needed for mixing increases linearly with increasing fluid velocity. When designing the microfluidic reactor, it was desirable to design so the mixing time increases weakly with the Pecklet number. The ultimate goal was to decrease the striation length across which diffusion takes place in order to mix more efficiently. The image on screen shows our experimental setup. 2 syringes loaded with liquid reagents are connected to inflow tubing and placed in a syringe pump. A clamp is used to keep the microreactor stationary on the test stand. Inflow tubing from the syringes are connected to the appropriate inlet ports on the microreactor. An outflow tube attached to the microreactor outlet ports leads to a waste beaker. An Arduino microcontroller and photocell are used to find the transmittance of the outflow. The photocell and light sensor are configured on the outflow tube so it can detect the transmittance of the product flow continuously as it is pumped through the tube. It is important to wear the proper personal protective equipment for the duration of this experiment. Nitrile gloves, lab coats, and safety glasses must be worn at all times. Be sure to review the SDS of malachite green and sodium hydroxide prior to beginning this experiment. The T-reactor and our second iteration, the serpentine reactor, were both rendered using SolidWorks. The decision to go with a serpentine design was based on fundamental reaction kinetics. Since we know that the reaction conversion increases as residence time increases, a reactor with a high residence time is favorable. A reactor with a long, winding channel will increase the residence time and thus increase the conversion. We also made the reactor channel narrower for the serpentine. The narrow channel will promote mixing by confining the reagents to a tighter space. Reactor designs were simulated in COMSOL prior to experimentation. The goal of the COMSOL simulations was to verify that our second design iteration performed better than the T-reactor before printing. This approach saved us time, printing materials, and reagents. Some assumptions that we made for the COMSOL simulation include the following. The reactor flows in the laminar regime, the fluid is incompressible, and the fluid has a diffusion coefficient of 1 × 10⁻⁹ meters squared per second. We used the surface average function to find the average concentration of product at the outlet. Once the outlet concentration of product was verified to be significantly higher than the T-reactor, the new design was ordered for printing. Reactor designs were uploaded as STL files to the 3D printers. They were printed with cross-linked epoxy, and the finished product was soaked in IPA. IPA was later pushed through the reactor to remove any uncross-linked material and to ensure there were no leaks or obstructions. Once the design was printed and ready for use, it was placed in the test stand. 30 milliliters of 1 × 10⁻⁴ molar malachite green was placed in one syringe, and 30 milliliters of 0.5 molar sodium hydroxide was placed in another. Both syringes were hooked up to the reactor and secured in the syringe pump. A specific flow rate was set, and a photometer reading was taken every 20 seconds once the components were flowing completely through the reactor. Trials were run with flow rates of 5 milliliters per minute, 10 milliliters per minute, and 15 milliliters per minute. A calibration curve was created to correlate photocell readings with malachite green concentrations. We originally conducted calibration using serial dilutions, but this proved to be problematic since the large changes in concentration caused the readings to be inconsistent. We changed to a linear calibration, where we made solutions starting with 1 × 10⁻⁴ molar malachite green down to DI water. Readings were highly inconsistent between each concentration. We believe that the initial malachite green concentration was more dilute than we thought, causing the data to have little change between each dilution. The experimental transmittance and the calibration curve relating transmittance to concentration were used to find the experimental concentration of Mg at the outlet. From this, we can calculate the conversion of malachite green using the equation X equals Ca0 minus Ca final all over Ca0. The plot of malachite green conversion versus residence time aligns with what we know about reaction kinetics. The conversion increases as the residence time increases. This is because when the residence time is higher, the reagents spend more time in the reactor and have more time to react and generate product. The plot of experimental conversion versus predicted conversion allows us to easily determine how the COMSOL simulation compares to the experiment. If a point on the plot is above the dotted line, that suggests the experiment overpredicted conversion as compared to the simulation. If a point on the plot is below the dotted line, that suggests the simulation overpredicted conversion compared to the experiment. In our plot, the serpentine points are vertical because the COMSOL simulation output did not differentiate between flow rates, which contradicts the theory. It is difficult to draw a conclusive trend from this plot due to the large amounts of error associated with our sensing technique. The issue lies more within the accuracy of the calibration curve rather than the precision of our experimental trials. If we had a perfect simulation matching the experiment, we would expect the points to all lie along the 1-to-1 dotted line. However, in practice, we would expect the simulation to overpredict compared to the experiments. This is because the COMSOL simulation makes simplifying assumptions that favor the reaction kinetics and more closely resemble an ideal space. The experiments should always perform poorer when compared to ideal conditions. The core conclusion we need to stress is that the calibration curve created is not physically possible. Conversions cannot go over 100%. Nonetheless, it was all that we had to go and convert photocell readings into reaction conversion. This problem could be mediated by making improvements to the experimental procedures, such as using a spectrophotometer to measure transmittance instead of an Arduino photocell, and preparing our own stock solution of malachite green to ensure it is the concentration that we expect it to be. We have reason to believe the malachite green available to us was of a much lower concentration than described, and this made our dilutions not what we expected. This is a two-faceted problem. The sensor for transmittance wasn't the tool needed for this experiment, and the dilution inflows for calibration were incorrect. Both of these problems were out of our control. We were able to show a few positive results despite the standout calibration problem. We confirmed that conversion increases as residence time increases, and we also demonstrated the principles of lab-scale reactor design. CAD rendering to design the reactor, simulation to predict the reactor performance, 3D printing for reactor construction, and experimental tests to determine reactor performance in practice.
What would you think if I sang out a tune? Would you stand up and